Okay, so we're recording. Picking up from where we left off last time, we finished cylindrical coordinates, and now we're going to do spherical coordinate integrals. And again, it's it is a change of variables. There is technically a pullback domain, but rather than pulling back the domain, we're going to push forward the slices. Right, and just like with cylindrical coordinates, just like with polar coordinates, we can see what those push forwards of the slices look like. Just a matter of thinking through the geometry. The good news is, even though these slices are kind of weird looking in spherical coordinates, what we're going to be doing is always using a particular order of the differentials. So we're always going to be looking at theta slices, which are pretty easy to draw. They're just these half planes hinged on the z-axis. Then we're going to be taking phi slices of our theta slices, because phi is second. And that's actually pretty easy to draw too. A phi, and let me zoom in where we can see better. A phi slice, like so, of our theta slice. Well, let's draw a phi slice. And how does that intersect? Well, the intersection of this cone with this plane is just this ray coming out of the origin. Like that. And then, how does rho vary? Rho being our inside differential, so our last slicing. Well, rho varies by just moving along that ray. So, even though the slices are kind of scary to look at in practice, and it's really not that big a deal. So as previously noted, this is always going to be our order. It just turns out that there are plenty of cases where there are other orders that are as good as this, but it's very rare for there to be an ordering that's better than this. So I say just always use this ordering, and asterisk. Technically, there's a few counterexamples, but in practice, day in and day out, real life scenarios, you're not gonna regret it. Okay, as with any change of variables, don't forget your stretching factor. Very easy to forget your stretching factor, especially since we're going to be drawing pictures and doing slices and trying to understand bounds and things like this, and the stretching factor sometimes just gets lost in the shuffle. My defense against this, my little life hack, is I always write this down. Correction, I try to make myself always write this down all at once, as if it's a single thing, which, by the way, it kind of is. This is dx, dy, dz. So please, along those lines, please don't ever write down just d rho, d phi, d theta by itself. What sense does that make? It's not a thing. Given that if you've been asked to compute an integral dx, dy, dz, d rho, d phi, d theta does not naturally have anything to do with that by itself. So why write it down? Right? It really makes a lot of sense to write down this whole thing all at once for this combination of reasons then. Okay, so let's dive in, start doing them. Here we go. Suppose we want to slice up this domain here. This ball of radius A centered up on the z-axis. And notice with, I want to do this in green, with theta slices being these planes, half planes like this, hinged on the z-axis. Those slices are just half disks. Everybody on board? And so for which values of theta do we get these half disks? Well, all of them, right? All the way around. I like to think of this as a consequence of the fact that part of the z-axis is entirely surrounded by solid. Or you might say this part of the z-axis is embedded inside of this solid. So that's gives us theta going all the way around. So 0 to 2 pi. Yeah, go ahead.
So just to be clear, these are theta slices?
These are theta slices, that's right. Fixed values of theta, constant values of theta look like this. That's right. Just like in cylindrical coordinates. Yeah. All right. Okay, so now we're going to fix a theta slice like so, and the problem with proceeding here is that this flat theta slice on which we're going to need to understand angles. We're looking at it from kind of the side which distorts angles. Right? This is confusing. So, for example, in 3D, that's a right angle. The way I have it drawn on the page, just because of the point of view we're taking here, it looks like an obtuse angle. Well, that's confusing. Right? So what I advise doing, this is just my own little personal hack, you don't have to do this, but I find it very helpful, is I will just redraw, back to this, we'll redraw the theta slice, just looking at it straight on. So this is the exact same theta slice that I had up here, just drawn looking right at it. And I find that's a convenient trick for seeing the angles a little bit more naturally and a little bit more comfortably. Okay, so now on to phi slices. Phi, of course, measured off of the positive part of the z-axis from the origin and then out at some angle like that. Right? That's what phi looks like. So in our sort of improved picture, there's the positive part of the z-axis down to the origin, a ray out like that, and you can see the angle, again, a little bit more honestly, a little bit more clearly, I think, in this bottom picture. Okay, so with that in mind, what is the range of values of these phi slices? Well, you just got to look at what you got and go start to finish. The first slice is going to be there, where phi is 0, straight up, right? The angle off the z-axis is 0 when you're looking along the z-axis. Right? And then, now phi goes along and it gets greater and greater and greater, and you can see now as the greater it gets, the shorter these slices are, and then eventually at pi over 2 is where they finally disappear. So ending value of phi then is pi over 2. Okay. All right. So we've got our theta bounds. We've got our phi bounds. We are now going to focus on a phi. Wrong color. Focusing now on a phi slice. Specifically, a phi slice of our theta slice. Right. So this is what we're looking at, and now we want to understand the range of values of rho. So okay. Well, apparently the first point is there. Don't forget what that point is. That point, this is just a convenient representation of what's actually right there, which of course is the origin, where rho is 0. So our starting value of rho is 0. Everybody buy it? Ending value of rho, keeping in mind, we're still looking on this phi slice of our theta slice. The last point is that point. And what can I say about that point? Well, again, don't forget, that's actually, honestly, some point up here. And I can see on my three-dimensional picture here that what distinguishes that is that it's on the sphere. So I'm going to have to take this sphere of radius a centered at 0, 0, a. I'm going to have to find its spherical equation. Of course, the way to do this is Algebra 2 gets us the rectangular equation, and then Chapter 1 methods allow us to turn that rectangular equation into a spherical equation. Now, I'm going to assume that you all are strong with all of that. Make sure you're good with your Algebra 2 equations of spheres and such in 3-space. And then also you're converting rectangular equations into spherical equations from Chapter 1. So just make sure you're algebraically good at that. And with that noted, keep in mind we're looking for a bound on rho. So in this equation, we need to solve for rho. Lucky break, it's already solved for. Don't get comfortable with that. It won't always be, right? But since it's already been solved for, there it is. It's my upper bound for rho, and that's that thing right there. Is everybody good? All righty. Okay, so there you go. So arbitrary integral on our given domain, I can rewrite as an iterated integral in spherical coordinates like this. Now look at how much time we spent talking about our slices and our bounds and spherical equations from rectangular equations and all that stuff, and wouldn't it be easy to forget this right here? Very important little factor, right? The stretching factor. It's got to be in there. Really is easy to forget when you get distracted by these other things. Again, the defense against that is to always write it down as you write down your differentials. Why wouldn't you? Again, this is what dV is. It's very natural to include it as you write down that whole thing. Okay, enough of that. Now pitch. I am a big believer in drawing good pictures. A couple of reasons. For one thing, it makes it easier to see what's going on, right? And you're going to be less confused by trying to understand the geometry, trying to see it all in your head. A picture is very, very helpful to that end. But I emphasize, that's not the only reason, right? Don't forget, you have to show your work and explain your reasoning. And if you look back up to what we did here, a very large part of our reasoning came from the picture, right? How did I know to write down the equation of a sphere? Because I identified from the picture that my upper bound for rho comes when I'm on the sphere, right? So the picture is unavoidably useful for the. In fact, I'm going to go stronger than that. It's essential, really, in the kind of reasoning that we're talking about here. So, since it's unavoidably part of the reasoning, you got to give me that picture. Okay, please don't try to save paper and fit a picture onto a postage stamp size piece of your page. There's a lot that needs to go onto the pictures. You might need several of these pictures. Go ahead and dedicate some space to this purpose. If you want to use the back of the page, keep in mind you're always welcome to use the back of the page on an exam. Sure, cool, go ahead, it's totally fine. Okay, alrighty. So I already said this, but you might need more than one, like I did in this example here. You might need to go through a revise and redo process. You've probably noticed this on the homework, that some of the things that you have to draw, they give you all these surfaces. And you're like, what does this solid look like? It's bounded by these things. And you draw the surfaces first, which helps you kind of see your solid, but it also makes for a messy picture. And then from that, you learn something about the solid, then you redo and make a better second picture. Sometimes you need a third, right, depending on how hard it is. So anyway, entertain that possibility. Do keep in mind, drawing is not a matter of, some people are just born with this talent, right? That may conceivably be part of the story, but is absolutely not the whole story. There are tips and tricks to learn. And I strongly encourage y'all to take advantage of that. And again, I have my own summary, my own tips and tricks are on my YouTube channel. Take a look if you like. It's on the Miscellaneous Topics playlist. You've heard me pitch that a bunch of times. It's everything that I know about mathematical drawing. I think it's good stuff. And then, in addition to learning the tips and tricks, it does take some actual practice. There's chops involved. Drawing a good circle, surprisingly hard. Right? Being able to draw straight lines and just general overall quality. You got to clock some hours to get the experience and get the muscle memory with your fingers and this kind of thing. Okay, enough of that. Okay, next example, another ball. Again, radius A. This time centered on the y-axis. Everything's a little bit different. Here is our solid, and we're going to be taking slices like this. These are our theta slices, and notice now, this does not surround any part of the z-axis. So we should not expect theta to go from 0 to 2 pi. So for example, values of theta over here where theta is negative, going that way. Swing and a miss, there's nothing over there. right? So you got to think about which values of theta, such as this one, which gives you a cross section that looks kind of like that. For what values of theta do you actually cut substantially into this solid? And I claim, and this is just a geometric appeal, it's going to be sort of the what you might call the right half of the picture. The part where y is positive. You're going to actually get substantial cross sections like that piece right there. So theta 0 to pi. Yep.
Would you demonstrate a little bit more about that? Because I'm struggling to see how it's from 0 to
Yeah, sure. So I'm going to show you the way I think about this, and I hope this helps. Let me give myself a little bit of space to work. So what I'm going to do is I'm going to look at this picture from above. I'm going to try to reproduce this, what we're looking at there, right here, but I'm going to look at it as seen from above. And as seen from above, we have an x-axis going this way, and a y-axis going this way, and then the z-axis is pointing right at us. Right, so I'm not going to draw that. My solid, let's see, the green solid there, it's a sphere. What does a sphere look like directly as seen from above? Well, it looks kind of like that, right? And now what do these theta slices look like? Keep in mind, they're half planes hinged on the z-axis. As seen from above, they're just kind of like this. Does that make sense? So this is just the picture, same exact picture, just as seen from above. And there's the first slice, and then my slices kind of go around like this. And then after a while, they start to get smaller and smaller, and they finally vanish there. So this is 0, and they've gone kind of I didn't mean to do that. They've kind of gone around. I'm just going to try to clean up as much of this as I can. They've gone around a half turn. So 0 to pi. Does that help? Yeah. A lot of 3D visualizing in these kinds of problems is, unavoidable. So, feel free on an exam, if necessary, to give yourself, an extra picture, kind of like this, to help you kind of think it through. That's all good stuff. Okay, yeah.
Does it really matter? Because it came up a little after t equals 0, like the plane that's parallel to z equals 0 to the x-axis. It's not actually touching this here.
Yeah, no, that I hear you. That's a valid point. So let's think that through. I mean, just by analogy, let's suppose that you're doing just a regular old double integral, and let's suppose that your solid looks like this. Right, we could make a similar complaint as I slice in the x direction. I have these substantial slices that look like this, and one could say that the first one, it's only a point. Does that really count? Right? Well, yeah, don't worry about it. It's just the one value, and it's going to have length of 0, so it doesn't matter anyway. But certainly anything beyond that point is non-zero in size. Right? And so I'm going to make the same argument here. You're right, and I'll do it on this picture here. You're right that, only positive values of theta will actually make a substantial cut. But the point is, any positive value of theta, no matter how small theta is, will make a substantial cut. And so the where it all starts is exactly at theta equals 0. Yeah. Okay, so we got 0 to pi. And now let's look at an actual theta slice. Let's see here. So it looks like I'm doing this in blue. So here's a theta slice. Again, redrawing the theta slice just for visual convenience. There it is. The cross-section disk I can see a little bit better. Again, as something like this. And so, okay, What's the range of values of phi? What does a phi slice look like? Well, phi, keep in mind, is an angle measured off of the z-axis at the origin. So over here in this picture, measured off of the z-axis at the origin. A phi slice looks kind of like that. So you can see various of our phi slices here, like this. And the first one, I mean, again, the actual phi equals 0 slice doesn't actually hit anything, but anything beyond that, however little beyond that, will make a substantial cut through it. So our lowest value, what we have to call our first value of phi, is 0. And then, moves along, various different values of theta, increases, phi increases. These phi slices keep getting shorter and shorter and shorter and don't actually end until you get all the way over to straight down, aka pi. So, range of values of phi, 0 to pi. There's our phi bounds, 0 to pi. Okay, and then fixing now a value of phi also. Now we think about rho, just going through our usual procedure. We start there. That point right there. Don't forget, that's just a shorthand kind of convenient perspective on that point right there, which at a glance you notice, hey, that's the origin. So, rho starts at 0. Looking at our rho bounds. And then let's see here, the last value of rho is going to happen, over at this point, which of course is actually over here. It's on the boundary circle of our slice, which geometric appeal is actually on the sphere. And so again, we've got to find the equation of the sphere. Again, you start by writing the rectangular equation of the sphere, converting to spherical coordinates. Make sure you can do that, right? This is all chapter 1 stuff, so review as needed. This case, it works out to be that. Again, we need to find a value of rho, so we solve for rho. Lucky break already solved for, and there you go. There it is. Everybody see the process? Okay. So the geometry is different in every example, and there's countless examples, of course. Right? But this process that we're talking through here is always the same. The differential is always in the same order. Notice, by the way, I wrote this down all at once, all at the same time, therefore ensuring I wouldn't forget my rho squared sine phi. Of course, this hack for making sure you remember your rho squared sine phi requires that you remember to do the hack. So there's endless circularity problem there, I suppose. But anyway, make every effort. This is what I do. I find that it helps. Yes. Great question. What we're doing here is we're focusing on what I like to call phase 2. So you remember, there's 3 phases of solving a triple integral problem. You've got step 1 is to turn whatever your application is into a triple integral. I'm assuming that's been done. So here, what is f? It depends on the application. Maybe we were computing mass, in which case f is density. Maybe we were computing the total quantity of pollution inside of all this air, in which case f is concentration. Whatever. It depends on the application. Does that make sense? Yeah. Okay. So all we're doing here is presuming that we have a triple integral and rewriting it as an iterated integral. And then we're also, you'll notice, not doing phase 3. We're not actually cranking this out, at least not in this example. All that, of course, is stuff that y'all already know how to do. Okay. All right. My last example is mostly on here for kind of the excuse that it gives me to make a geometric observation that I find very helpful. Here's the example that we're going to deal with. You see that this relates to a sphere. In particular, though, because of that greater than or equal to, we're looking at points outside of our unit sphere. So here's our unit sphere. we're looking at the points outside of that unit sphere. On the other hand, this, you'll recognize, again, this relates to a sphere, but this time, less than or equal means that I want points that are inside of whatever sphere that is, which is, this. So inside of the blue sphere, outside of the green sphere, and you got to think it through. What part of this picture qualifies as points that are inside of the blue and outside of the green, and it's just this business here. I always feel the need to shade in all the way. This is probably a little OCD on my part. There we go. So that's our domain. That's our R. Everybody with me? And I'm going to criticize my drawing now. My drawing is actually pretty inaccurate. There is actually a kind of a lip down there, and technically it does come all the way down to that lip. So why didn't I draw that down there? Well, here's the thing. While yes, there is a lip down there, if I were to fill in all of this also, then it just looks like I've got a flat-bottomed thing, which I don't. Right? There is a spherical-shaped scoop that's been taken out of the bottom of this thing, and this doesn't represent that at all. So it's actually pretty hard to draw this thing reasonably accurate. It's just a really hard shape. Some three-dimensional solids don't look good in two-dimensional form. So hard. How do we deal with this? And in particular, when it comes time to taking a cross-section, and keep in mind, of course, all we're going to do as we do things in spherical coordinates, we'll always start with taking a theta cross-section. How am I going to take a theta cross-section of something I can't even really draw in the first place? This is kind of a bummer of a situation to be in. So here's my big idea. I'm a fan of this. I think this is great. I'm gonna loosely refer to, if I can get this thing drawn, I'm gonna loosely refer to our solid, poorly as I have drawn it, as an intersection. It's the part that's inside of the one but outside of the other. Technically, it's the intersection of the top ball with the exterior of the bottom ball. But anyway, I'm just going to call it the intersections for lack of a better word. So that intersection, when you want to take a cross-section of it, right, I want to do a cross-section of this intersection. Neat trick. Step one, forget about the intersection business. Just look at the individual cross-sections. So, for example, I've got this sphere. Let's talk about what its cross-sections look like. This is an easy question. We'll get to the intersection business later. What is a theta cross-section of this ball? And it's a half disc. No big deal. I can draw that very easily. So inside of my theta half plane, there's my half disc. Nothing to it. Easy to visualize, easy to draw, no problem. Next, let's look at our other sphere. What's its cross-section? The blue sphere with the purple theta plane. Oh, half disc. Nothing to it. Right? And so the big idea is that if what you want is to understand how to take cross-sections of a very difficult to draw intersection, just instead look at the individual cross-sections and intersect them. And so I can come down here to my individual cross-sections we've already drawn. They were easy to draw. And let's take the corresponding intersection. So inside of the green, outside of the blue. Inadvertently, I've drawn it already. And so there it is. So even though it's very hard to draw the solid itself, this little hack allows me to draw the cross sections of this hard to draw solid much more easily. So I like this trick. I hope you'll find it useful, something to keep in mind. The rest of this question is pretty typical. It's a lot like other examples we've already done. I will point out that there is a real nice little move that we've seen before, and that is when it gets around to doing phi slices. Keep in mind your phi slices look like that, which intersect our theta slice like this. When you get around to finding the last one, the last phi slice, lucky break. This you can argue is an equilateral triangle, very much like we did for a similar example in polar coordinates. You just notice all three of these sides are radii of known unit spheres, unit circles, I suppose. And so equilateral triangle, that makes this angle here that I'm interested in, that angle phi is sort of obviously pi over 3. High school geometry and all that. So, nice little, every so often this comes up and it's a handy trick when you can. Okay. All right. Lots of examples that y'all need to take a crack at. They're on the exercises. Yeah, go ahead.
For the theta slices in this example, they go from 0 to 2 pi.
Correct.
Is that because they go all around the sphere?
Yeah, that's right. So our solid, as much as we can draw it reasonably well, this thing here, the way I like to say it is it entirely envelops and surrounds that part of the z-axis. All right, the z-axis is embedded into the, entirely embedded into the interior of the solid. And so, your theta slices, therefore, just have to go all the way around 0 to 2 pi. Yeah. Is that cool? Yeah. All right. Okay. So, there is another collection of ideas that I wanted to... Oh, yeah, go ahead.
I'm so sorry.
It's all right.
So, when you're taking your data, slices in general,
yep,
you're going from these the first to last in the direction of that given size. So kind of looking at the page where you had the translations, like data size, Z size, row size. This back here? Yeah.
Yeah.
So for something like the phi slices, it's like from the lowest, diagonal line to from the first diagonal line to the last diagonal line. So make sure to view them like that.
Yep, that's right. So that's right. So what you have here, this is a small value of phi, and this is a larger value of phi, and then this is an even larger value of phi. You can see these cones are kind of getting sort of wider and lower, etc. Right? And so, but what that looks like inside of a theta slice, which is all we actually care about, is it just looks like this. Just rays coming out of the origin at increasing angles off of the z-axis.
And do these slices go the negative y area?
Well, no. So they're entirely confined within. I mean, all we care about is what they look like inside of a y slice, right? And so it depends on which y slice you're talking about. The one that I have drawn here, this y slice only goes in a positive y, positive x direction. That was arbitrary. I mean, we could also talk about, here's this that I have drawn is theta equals negative pi over 2. So, yeah, that's fine. In which case, here's phi equals 0. There's a low value of phi. Here are increasing values of phi. And there's phi equals pi over 2. It just depends on which theta slice you're looking inside of. Yeah. All right. Okay, so we're going to move on now to symmetry theorems. This is, I feel, highly underappreciated. just, from my experience, and, how I used multivariable calculus in my, time as an undergrad, let's just say, and compared to how much emphasis is given on it in most multivariable calculus textbooks, I think there's a massive gap there. This is extremely useful. In particular, recall we have this theorem here from single variable calculus, which, arguably not super important in single variable calculus, but I hope you remember this one, that if you have a function that is odd, and if you're taking an integral over a symmetric domain, so when you flip it over, it's the same interval. So -6 to 6, or -5 to 5, or in negative a to a, right? If it's a symmetric domain, that integral is 0. Boom. Just instant. No calculations, no anti-differentiations, and plugging in the bounds and ensuing arithmetic. Nope. Just integral is 0. So I hope everybody remembers this theorem. It's an awesome little theorem, but it really kicks in value in 2 and 3 dimensions. And so just to give you a sense for why I think this is so important, I know a lot of y'all are engineers, and engineering is not that different from physics, and I did an undergraduate major in physics, and I took 9 physics courses in that physics major. And that was a lot of integrals. Y'all are going to have a lot of integrals too. Well, some of you are anyway. And tons and tons of integrals. Looking back on it, honest assessment, I think a conservative estimate of how many times I was able to just cite a theorem, multivariable version of this theorem, and say, oh, that integral is 0 by symmetry. I think about 20%. That's out of 9 classes, therefore, 1.8 physics classes worth of integrals. 0 by symmetry. That's a tremendously valuable. That was an unimaginable amount of effort that I saved myself by one trick, right? So massively valuable, and again, most textbooks, ours included, I believe undersell this. So I want to spend significant time on it. Reminders, what do we mean when we say a function is odd? We mean that if you negate the input, you get a negative on the output. Let me say that a little bit differently. If you reflect to the other side of the origin, the input, then you get a negative on the output. So for analogy purposes, this is going to be the useful way to think about it. Reflecting the input gives you a negative for the output. Okay. And what do we mean by a domain being symmetric? Well, I said something like negative a to a, but more to the point, a symmetric domain, if you have a point in that symmetric domain, then its reflection also in that same domain. It's just another way of saying that it's you do like this and nothing changes, and so it's from the negative of some value to the positive of that value. So equivalent ways of thinking about it. Okay. All right. So all we're going to do is extend this to a multivariable context. Real quick though, why does it work? Well, remember integrals are Riemann sums. Here I have my interval from negative a to a, so this is my symmetric interval. And let's look at the Riemann sum. It looks at the terms in the Riemann sum. Here's a term in the Riemann sum at some point p, and value of the function times delta x. That's the corresponding entry in the Riemann sum. And now let's look at this term in the Riemann sum. Well, value of f at that point times delta x. But notice, because the function is odd, this point, negative p, the reflection of p, I get a minus sign there. So in the summation, these two terms cancel. That's one point of view on why this, why this integral is 0 is because you're adding up a bunch of things, all of which cancel with another term in the summation. Is that all right? Okay. Now I'm going to give you a different point of view that's going to be more directly relatable to the multivariable use we're going to make of it, and that is, let's think of this in terms of a substitution. And remember, substitutions are just a single variable version of change of variables. So cosmetically, you're going to think, x is negative u, so well that's I've got x is a function of u. That's a sub. I mean, this is a u sub, basically. But specifically, yes, this is the specific u sub, but I want to think of this as being a change of variables. So here's how we capitalize on this. I've got a symmetric interval, which means that it is its own reflection. Reflect it, nothing happens. It's the same exact thing. I'm going to do a pullback because after all, I'm looking at an integral on an image. And when you have an integral on an image, you can pull back to an integral on the pre-image. That's the whole idea of change of variable pullbacks. Stretching factor, of course, is 1. It's just a reflection. That doesn't stretch or squish anything. And then lastly, plugging in, of course, g of u is negative u. F of negative u is the negative of f of u because of the oddness of f. And lo and behold, we're actually done, believe it or not. It doesn't look like it, but check it out. We've got an integral that we now see is the negative of itself. After all, this integral and that integral, it's the same exact integral. Different dummy variable. Nobody cares about dummy variables. It doesn't matter at all. This blue equation is literally saying that this purple integral is its own negative. And there's only one number that is its own negative. That is 0. Yep.
Go back to where you show the symmetry of I.
The symmetry, up here? Yep. Yeah, okay, so keep in mind what we've got here is this is just reflecting over the origin. So like if I have a value negative 3, when I reflect it over the origin, positive 3. Right? So now let's go up and look at this interval that we've got up here. We've got an interval from negative a to positive a. And let's think about what happens when I do that. If I take, every point I send over to its reflection. Every point goes to its reflection. But then likewise, every point over here goes to its reflection. Every point over here goes to its reflection. Altogether, when you take this whole purple interval, flip the whole thing, negative a to a, I mean, imagine you take this whole thing, flip the whole thing upside down, the result still goes from negative a to a. So it is its own flip. It is its own reflection. Does that make sense?
So what would a non-symmetric domain?
Oh yeah, non-symmetric domain would be something like this, where if I have an interval from negative 1 to 5. Right, when I reflect that, the negative 1 only goes to there. The 5 goes way over to here, and then the reflection of this green interval becomes that blue interval, not the same. Is that cool? Yeah. All right. Okay, so we're just going to do a two-dimensional version of this now. It's just same exact idea, just two-dimensional. And you'll notice that I've been talking about this, the idea of negating, as I'm thinking of that as flipping it over the origin, and I've been calling this a reflection. So, yeah, sure, this is a kind of a reflection. If you in a one-dimensional world, imagine 0 is a mirror, right? Then when 2 looks at itself in the mirror, and the mirror is at 0, 2 sees its reflection at negative 2. So likewise, I'm going to just talk about a two-dimensional version of reflections. Yeah, go ahead.
So sorry. Yeah. And then, so when we said that the integral is equal to the integral, but with the domain changes to g of I?
Uh-huh. Yep.
How could we do that?
Well, because nothing happened when I replace I with G of I. Because keep in mind, G just means reflection. Right? If you got an interval that when you reflect it, it's the exact same interval. It's still negative A to A.
So are you saying that G is just like, that's just a function that says what we're reflecting right now?
That is exactly what yeah, that's right. So G just throws in a minus sign.
So in theory, we could have said x equals to G of x, which is equal to negative x, which said it's a bunch of dummy variables.
I didn't follow. I'm sorry.
You just said x is just equal to negative x.
Well, but see, you can't say x equals negative x because you're kind of confusing your variables. You're conflating the input to this reflection function with what comes out of the reflection function. So you do need to give it a different name, right? So I can say when x is 2, then u is negative 2, right? But you can't have x be simultaneously both 2 and negative 2. It's just, you can't do that. Does that make sense? Yeah. So it's nothing to worry about with the dummy variables, just kind of a way of distinguishing inputs from outputs. Yeah. Okay. So here's the two-dimensional version of this. Instead of reflecting over a point, we're just going to reflect over a line. And what does it look like to reflect over a line? Well, if you have a point here, that point sees its reflection right there. So the act of reflecting moves x to r of x per this picture, and now, of course, the details, how do I find the formula for this reflection? It depends on the line. And there's lots of lines that I might conceivably want to reflect through. Depends on the situation. So, but independent of the details of the specific line involved, reflection will always look like this picture. We'll talk about how to actually find reflection formulas a little bit later. Today, depending on, we'll see. Ooh, it's already 4:16. Well, we'll talk about how to find reflections probably after spring break. But here's the big idea. The point is this reflection over the line, it's just like a negation in a single variable context. So we can talk about odd symmetry. Odd symmetry just means that if you reflect the input, then you get a minus on the output. Just like in single variable. It's the exact same idea, just generalized to 2 dimensions. What does it mean for a domain to be symmetric? Well, whenever you have a point in your domain, I need for its reflection to also be in the domain. Same basic idea. And with those ideas settled, here's our theorem. And it's just like the single variable theorem. Odd function, symmetric domain, boom, integral is 0. We're done here. I don't have to, take the usual approach to computing a double integral. Golly, I've got to slice it up and keep track of the bounds and get the bounds for my iterated integral. And then I'm going to have to do an antiderivative. And assuming I can do that antiderivative, I've got to plug in the inner bounds. That gives me a new integral and yet another antiderivative challenge. And oh my gosh, what a pain. That whole process, skip. Integral equals 0. Simply by checking 2 conditions. Now, it's a delicate theorem. You do have to make sure to check both conditions. My experience teaching this course for a long time now is a lot of students will see a symmetric domain and get kind of excited. Oh, hey, check out that symmetric domain. That's pretty sweet. And then forget to check whether the function's on. And if it's not, then the integral's not 0. Or it's certainly not, you can't argue it to be 0. This argument fails, and it just doesn't work. Right? So don't make that mistake. It's a very common landmine to step on. Secondly, make sure you're using the same line for both the oddness and the symmetry of the domain. It's got to be over the same line for the argument to work. And there's, again, 2 different justifications for this theorem. Domain is its own reflection. Change of variables pullback. Notice our stretching factor is 1. Oddness gives us this minus sign, and we're done. This integral is equal to 0. Very easy. It's just like with the argument we made for single variable. And we have proved that this integral is equal to 0. Or you can make a Riemann sum argument. That's not really what we're here to do. If you wanted to make a Riemann sum argument, again, you can just kind of argue, well, this term in the Riemann sum and this term in the Riemann sum are clearly negatives of each other. They are negatives because of the reflection and the oddness, and that minus sign makes them cancel. So we've got ourselves a powerful new theorem, and not enough time to do anything with it, unfortunately. So just to give you something to look forward to over spring break, we're going to, very first thing next time, we're going to compute this integral right here, which is a nightmare. Right? Look how ugly that integrand is. I see an e to the x squared. I'm already scared. But then there's also another factor, and there's the bounds are weird. This is a very scary looking integral. And what we're going to do, I don't even know if I can do this, directly. But what we're going to do is we're going to make a couple observations showing that the domain is symmetric, the function is odd, and then I'm just going to celebrate, boom, integral is equal to 0 by symmetry. And, drop the pen, walk away. So, details to come after spring break. I hope you all have a great break. See you later. And thanks for coming today. And so for those of you who couldn't make it listening on the recording, hope everybody has a great spring break.